So we're going to do some group theory today, and we're going to look at these three groups, evaluate what the group is in a Caley table, and we're going to see if they're cyclic and or abelian, so not necessarily they can be both. And then we're going to find the order of each element, and then each element we're going to see if it makes it into a generator of the group. So the three groups we've got here are U8 under action of multiplication modulus 8. So basically what that means is the numbers that are co-prime to 8, and then we multiply them modulus 8 to form a group. This one here is the integers from 1 to 6, and we're going to multiply them by 7, by modulus 7. And this one here is a symmetry group, and this is an equilateral triangle. We're going to find out if this one here is abelian or cyclic, and the generator and the order of each element. So let's start off with this one. So U8 under multiplication modulus 8. So first of all, we need to find the co-prime integers to 8. So these are 1, 3, 5 and 7. Okay, so let's just draw up our Caley table here quickly. 1, 3, 5, 7. 1, 3, 5, 7. And then we put the operation in here, multiplication modulus 8. Okay, so let's just go along the lines. So this will be repeated, as is this line here. So 3 3s are 9, modulus 8 gives us 1. 5 3s are 15, modulus 8 will give us 7. 7 3s 21, modulus 8 gives us 5. Okay, 5 3s are 15, modulus 8 is 7. 5 5s 25, modulus 8 is 1. And 7 5s 35, modulus 8 will give us 3. And here, let's bring this down in a better line. 7 3s 21, modulus 8 is 5. 7 5s are 35, modulus 8 will give us 3. And 7 7s are 49, modulus 8 will give us 1. Okay, now first of all, let's just work out the order of this group in each element. Okay, so the group itself is of order 4, so there's 4 elements. So the group U8 modulus 8 is of order 4. Okay, 1 is the identity element. We know it's the identity element because the outside is repeated inside the table. So 1 is the identity. So 1 is the identity, and this is order 1. Okay, so now what we want to do for the next 3, we need each of the elements we'll call A raised to some integer k, and we see what happens when we keep repeating them. So k equals 1, 2, 3 in this case, and 4 if possible, and we see if it can generate each member of the group. So let's start with 3 to see how that works. So 3 to the power of 1, that is 3. So modulus 8, that stays. 3 squared is 9, modulus 8 gives us 1. And then 3 cubed, that gives us 27. 27 modulus 8, we're back to 3 again. So basically we say is that 3 is order 2, because the power here, where we until we start repeating, is squared. So 2 is the order of 3. Let's have a look at 5. So 5 to the 1 equals 5, of course. Now 5 squared is 25. 25 modulus 8 gives us 1. So again, 1, if we're going to raise this again to the power, multiply by 5, we're back with 5 again. So 5 again is order of 2. Okay, now what about 7? So 7 to the power of 1 equals 7. That's fine. 7 squared is 49. 49 modulus 8 will give us 1. So therefore 7 is of order 2. Okay, so there's no element in this group which will generate all of the numbers 1, 3, 5 and 7. So basically what we can say is that this group is not cyclic. Now what about testing for abelian? Now abelian means if we have some A and some B element and we multiply them together, that also equals the converse. So B multiplied by A. So if we multiply 3 by 1, we should get the same as if we multiply 1 by 3, which is the case. Same here, 5 times 3 will give us 7, and 3 times 5 will also give us 7. Now there's another way we can do this. We can just draw a diagonal line down the centre there, and we see if the group is reflected. So 3 and 3, that's good. 5 and 5, that's reflected. Now we've got 4 7s here, so they're all reflected. The 5 and the 5, they're reflected, and then the 3 and the 3 are reflected. So what we can say is that this group is abelian. Okay, so now we'll have a look at this group here. The integers, multiplication modulus 7, and we'll go for the numbers on 1 to 6. So Z 7 under multiplication. So the elements of this group are 1, 2, 3, 4, 5 and 6. Okay, so straight away we can see, because it's got 6 elements, the group is of order 6. So let's write everything in this table here. So group order 6. Okay, now let's draw up a Caley table for this. So we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So now multiplication, modulus 7. So if we write that like that, that lets us know what the action is. So we could write the numbers in the top straight away. 1 is the identity element, so therefore we can just repeat it on the lines going down the side. That's how we can identify the identity. Okay, now what about picking up the parts of the Caley table here? So 2 times 2 is 4. Remember, we're modulus 7. 2 3s are 6. 2 4s are 8. 8 modulus 7 gives us 1. 2 5s are 10. Modulus 7 gives us 3. And 2 6s are 12. Modulus 7 gives us 5. Okay, so now with 3. 3 2s are 6. 3 3s are 9, which will give us 2 modulus 7, which then will give us 3 4s are 12, which give us 5. 5 3s are 15, which gives us a 1. And 6 3s are 18, which gives us a 4. So again, we're following the rules of a group where all the elements are not repeated, and we haven't gotten any repeated so far. So 4 2s are 8, which gives us a 1. 4 3s are 12, which gives us a 5. 4 4s are 16, which gives us a 2. 5 4s are 20, which gives us a 6. And 6 4s 24, which gives us a 3. So again, nothing repeated, that's good. So we know we're doing our calculations correct. 5 2s are 10, which gives us 3. 5 3s are 15, which gives us 1. 5 4s are 20, which gives us 6. 5 5s are 25, which gives us 4. And hopefully here we get a 2. 5 6s are 30, and that's a 2. So that also works good. 6 2s are 12, gives us 5. 6 3s are 18, which gives us 4. 6 4s are 24, which gives us 3. 6 5s are 30, which gives us 2. 6 6 36 gives us 1. Okay, so that's our group there. So now we're going to find the order of each of the elements. So remember, we've got the A to the K, and in this group one here, K equals 0, it's 1, 2, all the way up to 6. Okay, so 1 is the identity, that's just got 1, order 1. Let's have a look at 2. So 2 to the 1 is 2. 2 squared gives us 4. 2 cubed gives us 8, but remember we're modulus 7, so that gives us back to the 1. And then if you multiply this by 2 again, we're back to the 2. So this one is of order 3. So 2 is of order 3. Let's try the 3. 3 to the 1 equals 3. 3 squared gives us 9. So again, modulus 7, that's 2. 3 cubed, we can just go 2 times 3 for a shortcut. That will give us 6. 3 to the 4, we can just go 6 times 3 again, which gives us 18. And that gives us 4. And then 3 to the 5. Again, we'll just use the 3 to the 4 multiplied by 3. So 4 3s are 12. Modulus 7 gives us 5. And then all we need now is 3 to the 6. So 5 3s are 15. Modulus 7 gives us 1. So 3 is of order 6. Okay, so now we've come to a stage here where we've spotted a generator. So basically 3 will give us every element of the group. So 3 is a generator. So what we can do is just signify that it's a generator. We can write it like these, in these like larger than and smaller than signal. But for this we just make it into a set. So 3 is the generator. Okay, let's try 4. 4 to the 1 is 4. 4 to the 2, that gives us 16. That gives us 2. 4 cubed. So again, using 2 times 4, that gives us 8, which is 1. And then we know 1 multiplied by 4, we're back to the 4 again. So 4 is of order 3. Okay, what about 5? 5 to the 1 is 5. 5 to the 2 is 25. Modulus 7 gives us 4. 5 cubed. Again, use this 4 here. 4 times 5 is 20. Modulus 7 is 6. 5 to the 4. 6 5s are 30. Modulus 7 gives us 2. So this is looking good now. 5 to the 5. 5 2s are 10. Modulus 7 is 3. And then 5 to the 6. Hopefully this is going to give us 1. 3 5s are 15. Modulus 7, that's 1. So we know that 5, we can put that in also as a generator because it's of order 6. Okay. And then 1 we already knew. So what about 6? Let's have a look at 6. 6 to the 1 equals 6. 6 squared is 36. Modulus 7 is 1. So therefore we know that 6 is of order 2. Okay, so that takes care of that. So we can see that this group here has 2 generators, 3 and 5. The group is of order 6. So now I need to see if they're cyclic or abelian. Now remember what we said about abelian. We want any element A under multiplication by another element is equal in reverse. So let's have a look at a few examples here. What about 3 and 6? 3 and 6 give us 4, so 6 and 3 should give us 4. So that works. 4 and 3 gives us 5. 3 and 4 also gives us 5. So this is looking good. So again, use our little trick. Let's draw a little line down the diagonal and see if it's reflected in both sides. So here we've got 2 and 2. Here we've got 3 and 3. Here we've got 4, 6, and then 6, 4. Here we've got 5, 1, and then 2, and then 1, 5. That ticks the box for that. Okay, 6, 3, 5, 5, 3, 6. So that's repeated. And then here we've got 5, 1 along with the 2, and then 1, 5, 4, 6, 6, 4, and 3 and 3, and 2 and 2. So this group here is abelian. And as we've got 2 generators, this group is also cyclic. So it is cyclic. Now you've got to be careful here. When you've got a group that is cyclic, it is always abelian, but it doesn't always work out the other way round. So if a group is abelian, it's not always cyclic. So here we can see we've got evidence of this. Okay, so now we're going to have a look at the symmetric group under an equilateral triangle. So our group action here is multiplication. And now if you check in the link below, you'll see the description there for how we got to this group for the symmetric group of a triangle. So we did that in a previous video. So to save time today, I've just drawn up the Caley table already. So we need to find the order and the generator of this group. So let's first of all find the order of each of the elements. So remembering we've got A to the K, and this time this group here is of degree 6. So what we say is here, this group is degree 6. So this is degree 6. But the order is 6 factorial. Now if you check in the link below, again I will go through how we get to this. So first of all, to see the order of each element, we go pick each element A, raise it to the power of K, from K equals 1, 2, all the way up to 6, and see if we can generate the whole group. So picking E will always be of order 1, so that's order 1. So A to the power of 1, that's just A, that's fine. A squared, so that's A acting on A, that gives us B. So now cubed. So A cubed is equivalent of B and A. So therefore B acting on A, we will end up with the identity. So basically this one here is of order 3. So A is of order 3. Okay, what about B? B to the 1, yeah, that's going to be B. B squared, B acting on B is going to give us A. So B cubed is going to be A acting on B. So A acting on B will give us the identity. So therefore B is also of order 3. Okay, now let's go for R. So let's go here. Let's go on here. R to the 1. R to the 1 will just give us R. R squared, which is R acting on R, will give us the identity. So therefore what we say is that R is of order 2. And if we look closely at the group, we see that S acting on S is E, and T acting on T is also E. So T is also of order 2, and S is of order 2 as well. So we say that this group here is not cyclic. So let's write here, not cyclic. And next we want to test for abelian. So if we draw a line down here, we'll see if it's reflected. Well, we can see that this is reflected and this is reflected. But if we look down the bottom, we've got B and A here and A and B here. These are not reflected. So basically what we can say is that this is not abelian. So not abelian. So this group is neither. Okay, now one little thing we can just add in here. If we go split the direct symmetries and indirect symmetries, we can say that the direct symmetries here, they are abelian. And they would also be cyclic because every element inside there will be repeated, A, B and E. So they would be cyclic. So that little subgroup will be cyclic and abelian. But the whole group, i.e. the symmetrical on the triangle, is not. It's neither cyclic nor abelian.